Good afternoon, everybody. Now, before we dig in, I just want to get a quick sort of read of the room here. Who here does not have any experience with Elixir or Erlang? Okay. Who here does not have any experience with some sort of actor-based language where they have actors as a concurrency or parallelism paradigm? Okay. So just to get a little terminology out of the way, I'm going to be using Erlang and Elixir terminology, like Beam terminology, for talking about actors. In Elixir and Erlang, these actors are called processes, not to be confused with OS processes. They're an internal thing to the Beam, the VM, that these languages run on. And these processes are what they call actors. It's how they implement the actor pattern. And these actors communicate by sending messages to one another. And each process, each actor, has a mailbox, and those messages are stored in that mailbox. That mailbox is ordered, and they can selectively receive messages from that mailbox. So that is hopefully enough to get you all up to speed. So when I say a process, what I'm talking about is an actor in Elixir and Erlang terms. And when I say that we are spawning a process, that's again Elixir and Erlang talk for creating a new actor. They spawn a process. And I'm also going to be talking about parent and child processes. This isn't like a formal definition. I mean, it kind of is. But when I'm talking about parent and child processes today, I'm talking about a parent is one process that spawns other child processes. Because a big part of what we're going to be talking about today are the communication patterns between these actors and how those relate to certain patterns in working with parallel or concurrent computation. So, if you're anything like me, you may have come to functional programming of some sort, whatever language that you're using, because you're interested in concurrent or parallel computation. And this is awesome. But the thing is, concurrent and parallel computation, while easier in some ways in certain languages than in others, you still need to implement. And to implement these things, it's helpful to talk about certain patterns, because there are patterns that can be found in implementations of certain types of parallel or concurrent computation. And luckily, people are thinking about these things. A lot of the stuff that I'm going to be talking about today is taken from this paper, published back in 1999, quite a long time ago. It's a 20-year-old paper. And the thing I loved about this paper was that they were looking to give names to some of these patterns of parallel and concurrent computation. And one of the things that I learned, or I saw pretty quickly, I first had experience in object-oriented programming. And in object orientation, there are design patterns, and they are common, and they're shared across quite a bit of that world. People can talk about these patterns, and you know what you're talking about when you're talking to another programmer. And it's really helpful to have these shared sort of higher level abstractions, because it's easier for us to communicate when we're talking about patterns or problems in our code. And communication is really one of the hard parts of doing our job. So by having patterns that we can talk about, by having this sort of shared vocabulary, or what they call a pattern language, this makes, I think, one of the really hard parts of computing, which is the communication within a team or across teams, making that a little bit easier. Now, this paper they later turned into a book, which was published in 2004 by Addison Wesley. It's a great book. It has a great acronym, PPP, or 3P. I was sort of hoping that this talk, the title for this talk, would have a similarly great acronym, but then when I looked at it, I realized that this acronym was like kind of already taken, at least in the minds of me. I don't know, maybe millennials don't know what that is, but I always think of this, so it probably won't be referred to in that way. But in that paper, one of the things that really grabbed my attention was this chart. Now, this chart is not very high res, because it's, again, 20-year-old paper, so I made it a little, hopefully, easier to see. Now, what this chart does is we start at the top, and you answer sort of a couple questions about the particular problem you have at hand, and it helps to guide you through a couple questions to eventually a pattern that might be a good fit for the problem that you're trying to solve. And one of the things that I pretty quickly saw in this chart especially is some of the things that they recommend, some of these patterns, really didn't apply to me as an Elixir or Erlang programmer. And as I continued reading on in the paper, I realized that pretty quickly that these people were not solving the same kinds of problems that I am solving. Like 20 years ago, the people doing this research and thinking about these problems were thinking about them in a completely different context, right? Consumer multi-core processors hadn't even been released yet. The first consumer multi-core processors weren't released until like 2006, 2005-ish. And this paper predates that. So what they were thinking of when they were writing this paper were people writing programs to run on supercomputers like this to do massively parallel computations of stuff like trying to model, equations for theoretical astrophysics to try and simulate the beginnings of the universe, or doing weather models that will simulate the next 40 years of possible weather conditions. And clearly, they're not running Erlang on those machines. Like, they have very highly specialized languages that they're using that are very low level because they're trying to eke out as much of the computing power as possible out of those supercomputers. But even though I was a little bit dejected thinking like, oh, well, this isn't going to be applicable to me at all, I'm not going to get anything out of this, it turned out that there are still some good things. And that's why I think that even though some parts of what's in that paper aren't directly applicable to me as someone who writes mainly consumer applications, mainly for people to use on the internet, that there's still some stuff that I can get out of this that will help make my ability to communicate with my coworkers and other people in the community easier. And so, even though there are some things that we're not going to cover, we're going to cover some of these things. Now, that pattern down there, shared memory, Erlang and Elixir doesn't really have. Kind of, there's a way to do it, but we're not going to cover that today because I don't think it's particularly applicable to the kind of stuff that I was interested in and that I'm sort of assuming that many people in this room are also working on. This branch as well, this group by data branch, again, this is when you have data structures that are of almost unfathomable size that you need to process in some way, doing that sort of highly scientific computing, and you need to be able to parallelize computation over that data structure. That is also not a thing that people do building web applications typically, so we're not going to cover that today as well. This chunk here is a thing that does show up every now and then. So this is when you have some task that can be viewed as recursively parallel. A great example of this is the parallel compiler in Elixir. When you need to compile an application, it will attempt to compile each file in parallel, but because compilation can be viewed as a tree, you need to be able to sort of compile from the bottom up. And so you have a recursive data structure, you have a tree that can be recursively compiled. You're compiling this, which requires compiling those, and that can all be done in parallel. So even though that thing does exist and is a thing that a pattern, those two patterns do exist in Elixir and Erlang, because they're not as common and in the interest of brevity and fitting in the time slot, we're going to skip those for today. But these four remaining ones are awesome. And these you will find a lot. I think you'll find them in just about any consumer application. You'll probably find some example of at least 3 of these, maybe all 4. And that's why we're going to cover these 4 today. These are great, and I think being able to identify these 4 patterns and talk about these 4 patterns is going to make communication within a team and within a community a whole lot better and a whole lot easier. And what we're going to do is we're going to look at examples of open source code so that even though the examples that I'm going to be showing today are going to be simplified just so that we can get the important bits, all of the actual code is available out there on the internet if you want to go and take a deeper dive and look at the really interesting parts of implementing these. The first thing we're going to be looking at is Benchy, which is a benchmarking library for Elixir and Erlang, and that uses the reduction pattern. We're going to be looking at XUnit, which is the test runner and test framework for Elixir. That uses asynchronous decomposition. And then we're going to be looking at GenStage, which is a pipeline processing library in Elixir, and that uses pipeline processing. Now, you may have noticed that I said that there were 4 patterns, and there are only 3 examples up there, and that's because the 4th one is frankly so simple that it doesn't need that much code, that you can find it just about anywhere. And that also has the best name of them all, embarrassingly parallel. I just love that name. The canonical example of an embarrassingly parallel problem that I like to give is imagine that you are sending emails, right? So you have 20 emails, the same email might need to be sent to 20 different people, and you just send the emails, right? It's a very simple problem. You can send all of them in parallel. And one sort of implementation of this might look like this, where we are mapping over some list, some collection of emails, and we're sending each one with that send email function. Now, doing it this way does it in series. We send one email, and then the next, and then the next, and there's no benefit to parallelization. But on Elixir, with Elixir and Erlang, to make that parallel, that's it. That's the only difference, is we are spawning a process to handle the sending of that email. And the parent process continues on once that spawn is finished. And then the parent process, the child processes that we've spawned go and send the email, and they do their thing, and then they go away. And that's it. That's the whole pattern, is that you spawn some child processes to do something, and it goes away. Now, if you're anything, again, like me, pictures sometimes help, and I like drawing pictures, especially to sort of explain communication patterns. So we're going to look at some pictures today as well. Hopefully that'll help everybody see these patterns, because that's what we're trying to do, is identify and name this type of pattern. So here, we have our parent process, which has 3 emails that it needs to send, and to do so, it spawns 3 children. And each of those children gets 1 email, and it sends its email, and then it goes away. It exits. And that's it. We're done. That's a really simple pattern, but it's super common as well. There are a lot of these types of problems that can be seen as embarrassingly parallel. And luckily, in many actor-based languages, or languages with actor-based parallelism or concurrency frameworks, you can do this really, really simply. Now, I also want to give a little overview of each of these patterns, because the thing is, each of these patterns have these sort of unique types of problems that they are associated with, so that when you see a problem that meets these criteria, you can know, oh, that looks like a problem that we can solve with this pattern, with the embarrassingly parallel pattern, or this looks like an embarrassingly parallel problem. So, for something to be a good fit for this pattern, we want an eagerly evaluated linear input. We also need to make sure that there's no communication from the child processes back to the parent process. Right? The parent spawns the child, and then the child doesn't send any messages back to the parent. There's also no communication between the siblings. We'll see that in our example, those child processes were not sending messages to each other. They just did their own thing. They were totally independent. And by totally independent, I also mean that there's no shared dependencies between any of those child processes in doing their work. If there are shared dependencies, you're pretty quickly going to run into a race condition of some sort, and that's going to be a bummer. So if you have shared dependencies between your child processes in some fashion, this is not going to be a good fit. Okay? Now, the next pattern is very similar, but with one major difference. You may know this pattern by a couple other names, actually, because it's a very common one. I would say this is maybe even the most common pattern. This is also frequently seen as something called async await or map reduce. What we're doing is we are doing some work in parallel, but then there's an additional step. There's a reduction on top of that. And so what we're going to look at here is this code, which is basically a parallel map. So this is real code from Benchy, because you can do stuff in parallel in Benchy, and they write a little parallel map function there. And basically what we're doing is we, again, are mapping over our inputs, but we're using this function in the Elixir standard library called task async, which will execute a task asynchronously. And what it does is it returns a ref. We'll learn a little bit more about that in a second. And then it takes those list of refs, those references, and then it waits for each of those. So the wait is synchronous, that's blocking, but the map step is asynchronous. So that's in parallel, but then the reduce is in series. So because I'm pretty sure most of you don't know what's going on in that function, we're going to dig a little bit deeper into the Elixir standard library and see, again, a very simplified version of what's happening there. So in that async function, the first thing we're doing is using a built-in function in the VM called makeRef. Now, this reference, is a native data type in Erlang and Elixir, and you can think of it as a unique value. It is functionally a unique value. It's pretty much guaranteed to be unique. So for each of these tasks, it gets its own unique value. Then we capture a reference to the parent process so that the child processes know where to send their message when they're done. And then we spawn a new child process and say, hey, child process, please send me, so that's the send command that says send a message, send me a message that is a tuple with that reference, that unique value that I gave you, and then the output of executing this function that I'm giving you. And then we return that reference. So that function will start that child process, and that child process knows what to do when it's done to send its return value back to the parent. And then we return that reference, because we're going to use that reference in the await function. So what we start here is a receive loop. This is where the parent process, or any process, is sitting and waiting for a message that will match a pattern in its mailbox. Like I said, it can selectively receive from messages in its mailbox. So it's waiting to receive a message that matches a pattern. And when it gets a message that includes that unique reference that we're waiting for, it will receive that message, process it, and return the value that came with it. And that's the value that was calculated asynchronously in parallel by our child process. And with receive loop, because I said that's blocking, it will sit and wait. The process won't do anything. You can set a timeout if you like, so that if you're saying, after 5 seconds, boy, that thing should have finished, and if it didn't finish, something might have gone wrong, so let's just move on. We're not going to wait any longer. You can set a timeout there if you like. So as we see, that map is done in parallel, but the reduction part, is done in series. And I just want to give 2 other quick examples to show this, because this is basically what makes this pattern. So here's a quick example. We have a function here, and that function's job is to wait for some amount of seconds to simulate some expensive work of varying time. And then when it's done, it's just going to send the current second. So what time it is, just the second, back to the parent process. Then we can start with the current time, which is 48 seconds, and then we parallel map over those numbers. So we're going to wait for 1 second, and the second one will wait for 2 seconds, the third one will wait for 3 seconds, and the fourth one will wait for 1 second. And then it will send the time that it finished at back to the parent. So it's as we expect, 49, 50, 51, 49. So it's not 49, 49, 50, 51. The reduction is done in series, okay? That's the important bit. And then, of course, we're done at 51 seconds. That's when that parallel map finishes, after it's received all of the messages from all of the child processes that it spawned. And in pictures, if this helps, it always helps me, we have, again, our parent process, and it spawns our 4 child processes to do their work, their calculation. And then when they're done, they send their messages back to the parent. And then they go away. They exit, and they get cleaned up by the garbage collector, and that's it. It's a pretty simple pattern, but it's a really, really powerful one, because it allows you to essentially do work in parallel, but then to get some reduced value of all of that work in parallel back to the parent process. Whereas with embarrassingly parallel, you didn't get anything back to the parent process. You just did the work and didn't care about the result. Here, we care about the result. That's a big difference. Now, this next thing I'm going to show is technically unrelated, but it's so cool, I always love showing it. So this is our basic async and await. And with this, I can chew up every CPU cycle on whatever computer I am using to execute whatever parallel computation I want, right? As long as I have it set up that way, I can make sure that the Beam, the Elixir VM, is using 100% of all CPU cores. But what if I wanted to use 100% of all CPU cores on 10 machines? What if I wanted to distribute this problem? Well, that's it. That's the only difference. I love showing this because it's such a clear example of that saying that when you have parallelism with actors, that you get distribution for free. I mean, clearly there's a lot of stuff that are, distributed programming is hard. There's a lot of other edge cases and things you would want to handle, and actually setting up your mesh, setting up your cluster is a thing. But when it comes to actually distributing and doing the work, that's the only difference. It's pretty much there. And that's so cool, and that's why I always love seeing it. But back to the important bits. Reduction. What sort of problems fit this pattern really well? With reduction, we still have an eagerly evaluated linear input, but the big difference is now we can communicate back to the parent. The children can send messages back to the parent. We're still not sending any messages between the siblings, between those child processes, and there's still no shared dependencies between those child processes. If you have some sort of shared dependency, things are not going to go well. But what about when we have an input that isn't eagerly evaluated? What if we have some lazily evaluated input? How do we handle that? Now, this is one thing that, especially on Erlang and Elixir, with Erlang and Elixir and on the Beam, I'm assuming in most other functional languages as well. You're probably not manually managing memory, but this is one advantage where we have it way easier than the academics using these very low-level languages where they're manually managing memory. Being able to efficiently process some input of unknown size when you're manually managing memory is a real difficult problem. It's a lot easier for us, luckily. But I think it's still important enough to go over this pattern and give it its own name because it is a different thing. And what they call it is asynchronous decomposition. So we have something that we're decomposing, but we're doing it asynchronously. We don't have the full thing that we're processing in parallel before we start processing it. So what we're going to look at is the test runner for XUnit. In XUnit with Elixir, you can run some of your test modules in parallel if you like to speed up the execution of your tests, which is great. You don't have to do it for all modules. You can just tag certain modules and say these can be run asynchronously. And you can have other modules that are run synchronously. But this is the basics of the runner. The module sort of looks like this. We have a run function, which, as you would expect, runs our tests. And then we have a loop. We have an async loop and a sync loop. And then we have a function to actually run the module, and then we have a function to run each test in the module. But let's dig in a little bit deeper, and we're going to start seeing something pretty interesting. So the first thing that we see is an event manager. So we have that event manager start function. And what that's going to do is start an event manager. An event manager in this case is a process. It's another actor. And its job is to basically receive a whole bunch of events. Now, technically, we don't need this event manager for this pattern. This is just the way that XUnit does it for a lot of reasons. But we're thinking of this event manager as basically a parent process. It's there as an optimization to separate that event manager from the actual parent that's running our tests. But it's not needed. So when we look at the pictures, we'll see that that's on the same level as the parent process. And when we talk about the communication patterns, you can think about this as a parent. So we start that event manager, then we tell it that we've started running our test suite. Then we enter a loop to say, let's run some stuff. And then when we're all done, we again send our event manager, execute another function that sends another message to our event manager saying that the test suite has finished running because it's keeping track of the times and stuff. Then we get all the results because it's also been keeping track of all the results of all the tests as they've been running. And we return those results after we tell our event manager, thank you very much, you've done a great job, you can be shut down now. But then the real fun part is this. This is where we have our asynchronous decomposition. So in Elixir, the test modules themselves are not compiled at compile time. They are EXS files, which means they are functionally interpreted. They're scripts. They're compiled after the VM has started running. So these are compiled asynchronously. And in order to make things a little faster, we're compiling all that stuff in parallel, and then the parent process doesn't know how many of these modules need to be run. It's just sitting, again, waiting for one of these to be ready. So it doesn't have all of the stuff that it's doing in parallel before it starts doing its work. It's asynchronously decomposing some structure, some list, some group of things. And what it does is it's going to sit and it's going to wait for a module to be ready, and when it gets one, when it receives a message that a module is ready to be run, and if it's an asynchronous module, then it spawns a process to go ahead and run that test module. But again, asynchronously. So the minute that is spawned, it goes back waiting for another module to be ready. And then it spawns another one. Eventually, it will go back into the loop, do its thing after it spawns that process, and then eventually it will get a message saying that, okay, it looks like we've got all of our asynchronous modules. And so it enters the synchronous part of the loop, which is pretty much the same, but again has asynchronous decomposition. These modules are still compiled and loaded into the Beam code server asynchronously. And so when these modules are ready, it gets a message saying, okay, you got another module you can run now. But the big difference here is this is run in the parent process because these cannot be run in parallel. Sometimes you have some tests that might have a shared dependency between them, and if you run them in parallel, you will have flaky tests and problems, and you don't want that. So you can run your tests in series if you want. So here, it's not spawning a process. It's doing those in the parent process. And then after it runs one module, it goes back into the loop, waiting for another module to be ready to be run. And then again, eventually, it's going to get a message saying, okay, we've done everything. We've finished asynchronously decomposing all of the tests. All of the tests that are going to be run have been run, and so it exits, and it just says, okay, I'm done with the okay atom. And just to sort of show you a high-level idea of what's going on when it's running those tests, pretty simple. It's again sending messages to that event manager, so that's coming from one of the child processes or from the parent process, and saying that we've started running a module because it's keeping track of timings again. And then it just maps over all of the tests in that module. It says, you know, give me all the tests that are in this module, runs each of them one by one, and then when it's done, it sends a message back to the event manager again saying, okay, we're done. And then running a test is as simple as you would think. It again sends messages to the parent process to say, I've started running this test because it's keeping track of timings, and then it sends the result of running the test, whether it passed, failed, errored, skipped, whatever, and then it's done. So that's what's going on, and hopefully this will make a little bit more sense in pictures. So we have, again, our parent process, and the first thing it does is it spawns that event manager. And that event manager is going to sit and listen for events. And while that event manager is listening, that parent process gets a module that's ready to be run, so it spawns a child process to execute the tests in that module. And then it goes back to waiting. And that child process does its own thing. It's running those tests the whole time. And then the parent gets another message saying, here's another module ready to be run. So it spawns another child process to run that module. And then eventually the parent goes back to waiting. But now one of the child processes is done. It has something to send back to the event manager. And so it can send messages up to the event manager. Okay? And then it goes away when it's all done. And then maybe another one's ready to be run. And then the children keep sending messages back up to the event manager when they have a message to send, when they have results or some other timing information back to the event manager. And then at the very end, our event manager gives the results back to the parent process and gets shut down and goes away and does its thing. But that's the idea, is you have those two levels, and the children can, again, communicate with the parent. So it's very similar to reduction. But what we have with asynchronous decomposition is the big change is that first thing. We now have a lazily evaluated input of functionally unknown size. We don't know how big it is. But we still have communication with the parent allowed. So in this case, that parent could be the event manager at that level, or it could just be the parent process itself. XUnit happens to use an event manager in that case, but it functions as a parent. It's on that same level. There's still no communication between the siblings, we saw. So those siblings, the work that they're doing, those child processes, they're still independent. They don't need to coordinate. There's still no communication, and there's still no shared dependencies. If you try and run your tests with shared dependencies, it will be an unfortunate situation. You'll get flaky tests. It's no fun. Now, could we simplify this? Could we use reduction to solve this problem? Yes, we could. We could eagerly evaluate the compilation of all of the test modules, and when all of them have been evaluated, we can sort of separate the asynchronous ones from the synchronous ones, and we can do it as reduction just fine, and we can use that parallel map function that we saw earlier to do this thing. We could do this as reduction. But what we're losing is a little bit of efficiency. So we need to first compile everything before we start running our tests. Whereas with asynchronous decomposition, if some test module takes a really long time to compile, you don't have to wait for it. You can start running all the other test modules, and that's a nice little speed up. That's a nice little benefit there. So that is the sort of trade-off in this case. But also, one of the reasons that I really like having asynchronous decomposition as its own named pattern, with that big difference being that the input is lazily evaluated, is it's a nice input, a nice lead-in to that fourth pattern that we're going to talk about, which is this pipeline processing. Now, this is what it sounds like. Pipeline processing is a fairly, I would say, common thing in many applications, or even seen at a larger level if you have many services that work together. There may be pipelines where data travels through one service, then another service, and using queues and such for doing that sort of thing. But this is also really helpful to do within a given application, within a single running application, having some sort of pipeline processing for data. And what this pipeline processing does is it allows us to sort of deal with that thing that we haven't been allowed to deal with yet, which is shared dependencies between the child processes and communication within the child processes. And the other sort of caveat to this, though, is this can get very complicated to do well. To do this at a very simple, in a very simple way isn't too hard. But there are a lot more edge cases because this is a much more complicated and difficult problem to solve. And so if you're going to reach for this pattern, if you're going to use this to solve a problem that you have, I really, really highly recommend not writing your own code to do this. I think in many mature ecosystems, you're going to see some sort of really well-designed library that will do this for you, that avoids a lot of the edge cases and handles a lot of the common problems. So please, I encourage you, reach for one of those. And with that caveat in mind, I'm actually not going to show the code because it is kind of complicated. I think we might be able to understand what's going on, but luckily this is open source. So if you do want to go and read the code, you can. The library is called GenStage. It's on GitHub. And you can see how that implements this pattern. But it's a lot of code. It's a complicated problem. And it's a complicated problem to solve well. But what I do still want to show is the communication pattern, because that communication pattern is different from what we've previously had. And now we have our parent process again, but this time we're labeling it with an S as a supervisor. A supervisor is a thing in Elixir, in Erlang. They have a framework called OTP, which allows for supervision of processes. And basically, I wanted to change that because we have something else that's going to get a P in this, so I didn't want to confuse folks. So now we have our parent, but that's a supervisor. And what it does is it spawns 4 processes, 4 child processes. And each of these processes represents a stage in computation. Hence the name GenStage. It stands for generic stage. That sort of naming paradigm is a thing you see in Elixir and Erlang very frequently. Now that first one, way over on the left, that P, that is a producer. That produces data. And then the fourth one, way over on the right, the C, that is a consumer. That consumes data. And then the 2 in the middle, the PC, those are producer-consumers. They both produce and consume data. And so when you're designing your pipeline, you have to think about the stages in which you are transforming or modifying or working with your data, and to decide where you might have shared dependencies, what can be done in parallel, what must be done in series. You know, you're looking at a much more complicated problem, and you're dividing it up into these stages, and then these stages communicate in order to do their job. Now, because GenStage solves one of the more common gotchas in this sort of thing, which is back pressure, the communication pattern amongst the children actually starts way over at the consumer. So the right over there. It starts at the consumer, sending a message to the producer that it has subscribed to, saying, okay, I'm ready for some data now. I can do some work. Please send me some data. And then that producer is also a consumer, and so it sends another message back down the chain and back down the chain until we get to a producer, which sort of starts our chain and says, okay, I will get some data for you. Maybe it already has data ready to be given. And so it sends some data to the second stage, some event or some data. And when it's done, it still remembers that this next one wanted some data when it was ready, and so it sends it back along the chain, and it sends eventually back to the consumer. So it uses back pressure to avoid a really common thing, which is the ability to maybe overflow or overwhelm one stage in the process, and you can have really bad things happen if that happens. So that's why I say please use a really well-designed library for this type of thing, because it will help you avoid those common pitfalls. But that's the idea with pipeline processing, is you have this sort of pipeline and you have communication between the stages to send data when it's ready to be processed in steps, in stages. And the pipelines could be far more complicated than this. You can have multiple children at a given stage, so you can design for whatever you need. If one of your stages functionally, on average, takes far longer than one of the others, you can have multiple workers in that stage. So this is a really, really powerful paradigm. It's a really, really flexible pattern, but it's complicated. And that's the trade-off we're making there. But what we get is a pattern that helps us deal with lazily evaluated inputs of functionally unknown or potentially infinite size. And the communication with the parent is still allowed, although in this case it is rare. Often it's more seen as in supervision strategies that children can send messages to the parent if something crashes and needs to be restarted, things like that. So with pipeline processing, that communication back up to the parent is a little bit more rare, but it's still allowed and it still does happen. But there is a lot of communication between the siblings now. And now, because we have that communication between siblings and we can design our pipeline in such a way to avoid problems with these shared dependencies, we can solve problems where there are shared dependencies between the children. We just need to remember to design our pipeline in such a way as to deal with those dependencies. So, in summary, because this is the biggie, is we have these 4 different aspects of a problem, and we need to know if I have a problem that has this sort of shape, that has these attributes, what is a good pattern to help solve this? So, for our embarrassingly parallel pattern, we have eagerly evaluated input, but no communication with the parent or between siblings, and no shared dependency between the siblings. If we need communication with the parent, that's where reduction comes into play. So we still have an eagerly evaluated input, but now our children can send messages back up to the parent, but we still don't have communication between the children, and we still don't have shared dependencies. With asynchronous decomposition, we're now dealing with lazily evaluated inputs of functionally unknown or potentially infinite size. But it still looks a whole lot like reduction. We can still send messages back to the parent, but we still don't send messages between the child processes, between our children actors, and we still don't have shared dependencies. If we want to solve that very difficult problem, that's where we can reach for pipeline processing. We now have a lazily evaluated input of functionally infinite size, but we can communicate with the parent, and the children can communicate amongst each other. And you can deal with the shared dependencies in that work with that communication and with the structure and the design of your pipeline. So those are the 4 big patterns that I wanted to cover today that I think are seen pretty frequently in a lot of consumer applications if there's an actor-based concurrency or parallelism pattern there. These are all things that I use all the time in Elixir and Erlang, and have used quite a lot for the last 4 or 5 years that I've been working with that. And I love the idea of being able to just talk with another developer on my team and say like, oh, that problem looks like something we can use reduction for. And we know what we're talking about when we say that. We know what that pattern looks like. We know how to implement it. We don't need to spend 20 minutes getting on the same page about what that means. Having this shared vocabulary is really super helpful. So I hope that all of you all, going back to work next week, can maybe talk to your coworkers, or if you're not at work yet, if you're still in university, you can maybe talk to folks. And I'd also love to see more research about this. I mean, I know that there are a lot of people doing more research in this world, but it's a lot of that research is still in the very, people doing the really, really hard problems, and not the people that are doing like kind of the scientifically easy problems, but the hard problem, I think, is always communication. So the more that we can have better ways of communicating about these sorts of patterns and these sorts of problems, the better our applications are going to be. I want to give a thank you to Sketch, my employer, for supporting me in coming and speaking today. We are hiring for Elixir positions, so if that's something you're interested in, please come talk to me. We can chat about that. Or if you just want to talk to me about other stuff, totally, I'm around, and I love talking to folks. So come say hi, and thank you all. I think we might have some time for questions, but yeah, thank you. That's it.